Thank you for the introduction. Okay, I'm going to start by defining attribute-based encryption. So in attribute-based encryption, there is a master authority. In my example, it's going to be a university. And this university provides secret keys to the users of the system. For example, we have a student in a PhD student in mathematics, the first user. So his secret key contains the attributes PhD student mathematics. Different users may have different keys. And yeah, that's it. So now think of the following situation. There is a professor who has a file that wants to share with some people at the university, and in particular, she's thinking of certain policy. For example, she wants to share this file with professors or PhD students in mathematics. So what she can do is to run this attribute-based encryption algorithm and produce a ciphertext that this ciphertext can be public now, and only those who own a secret key whose attributes satisfy the policy will be able to decrypt. In particular, in this example, only the first user will be able to decrypt. A very important requirement in attribute-based encryption is that is what is called collision resistance. So we want these two other users to not be able to combine their keys in order to decrypt together, since she's a PhD student and the second user studies mathematics. Okay, so this is the setting. More formally, attribute-based encryption consists of four algorithms. The setup, that in our example was run by the university, and it allows you to produce a pair of keys, the master public key, the master secret key. The key generation, that was also run by the university. In our example, it was run 3 times, one to produce one of the 3 keys. And this requires the master secret key. That is why only the university can run this algorithm. So this abstract value y, in our example, corresponds to the set of attributes associated to the key. Then there is the encryption algorithm that was run by the person on the left. And on input, a certain policy that I represent by X and certain message, it produces ciphertext. And decryption is going to work only if certain predicate associated to the ciphertext and the key holds. Okay, so there have been a lot of works about ABE. Of course, I'm not showing all of them, only some of them. It all started with this work by Sahai and Waters in 2005 with a fuzzy identity-based encryption. So in this picture, I also want to highlight these two works because they allow to make attribute-based encryption in a modular way. So actually, all the previous works were focusing on a specific predicate, like the inner product equals 0 or something like that. And these two works significantly improve the expressivity of the schemes that you can generate. And I also want to mention this work by Agraval and Chase from Eurocrypt this year, because one of our results was inspired by this work. All right, so almost all existing primitives about attribute-based encryption use bilinear groups. A bilinear group consists of 3 groups. G1, G2 are called the source groups, and GT the target group. And there is this efficient pairing that allows you to compute, roughly speaking, a multiplication in the exponent. It satisfies that formula. Well, it's also said that this pairing is non-degenerate. So basically, that element GT needs to be a generator of the target group. So as I said, almost all primitives about AB are built over bilinear groups. And they are not, so the state of the art is not very satisfying in my opinion, because you usually need many group elements to encode policies. And not only that, but so the running times are on the magnitude of seconds. So for example, to encrypt a policy of 100 attributes, you may need 2-3 seconds for the most efficient schemes. So it's a very interesting problem to improve the efficiency of attribute-based encryption. So here are our contributions. In this work, we provide a new framework for analyzing cryptographic constructions in the generic group model, GGM. And this is an idealized model that captures the absence of generic attacks. So basically, this model provides minimal requirements of security. What you are proving when you prove some security in the GGM is that there does not exist an attacker that works for every implementation of the group. So of course, this is not the standard model, but it's some level of security. And this framework is new in the sense that uh, we can deal with divisions in the exponent. So there are some previous works about this, but they don't consider this class of schemes. Okay, in this work, we also provide an automated algorithm and an implementation to check the security of candidate constructions. And we also provide some, we also present some new constructions. I want to distinguish between constructions that are really new, like they don't appear in the literature, and other constructions that we present are just adapted from existing constructions. So usually these constructions are proven secure over composite order groups, because proving security over composite order groups is usually easier. But no one knows how to formalize their security in the standard model over prime order groups. So what we can do with our framework is to show that they are secure in the GGM, which is at least some requirement of security. And since prime order groups are supposed to be much more efficient than composite order groups, well, you can implement these primitives and at least you know that they will be secure in the GGM. So this is how the security analysis works. So if you have a attribute-based encryption candidate and you want to analyze it in the generic group model, this you will have what we call the experiment in the generic group model. And the first step is to show that this experiment is negligibly close to symbolic experiment. So the difference is that in the generic experiment, you may sample two values, X and Y, and there is a certain negligible probability that these two values are equal. And in the symbolic model, you don't sample, you just have two objects that you call X and Y, and these objects are never equal. So you need to show that these two experiments are indistinguishable in the sense that no algorithm can distinguish between the two. And this is done by our master theorem. And then the last step of the proof is to show that no adversary can win the symbolic experiment. So actually what we show is that a certain system of constraints is unsatisfiable. And this is what we can do with our tool. Okay, so I'm gonna illustrate how this works with an example. This is a primitive adapted from a work by Hotek Wee, and it's about identity-based encryption, which is a special case of attribute-based encryption. In particular, in identity-based encryption, you encrypt for an identity, and users have a key for an identity, and the identity needs to match in order to decrypt. So in this example, identities are going to be ZP elements, integers modulo P, and the messages are going to be elements in GT. So I want to point out that this primitive has been proven secure by Hotek in the composite order group and the standard model, but it's an open problem to prove it secure over prime order groups in the standard model. So I'm going to define the primitive. So in the setup, you sample two random values, alpha and beta, and that you keep as a secret in the master secret key. And the master public key includes a GT to the alpha and G1 to the beta. Key generation just outputs this group element. So it's a generator of the group 2 to the power of alpha over beta plus the identity. Note that in order to compute this group element, you need to know alpha and beta. Encryption samples a random value, S, and computes these two group elements. The first one is in G1, the second one is in GT. And note that the second one includes the message multiplied by some factor. This is usually known as the blinding factor. So in order to decrypt, you will need to compute this blinding factor and divide by this group element by this factor. So okay, actually, I'm gonna decryption works like that. I'm gonna quickly show why it works. So you put the second element of the ciphertext divided by the pairing of the first element of the ciphertext with a secret key. Okay, the first element can be rewritten like that, and now we can use the properties of a pairing in order to move the exponents outside. And now, if the secret key was for the same identity for which the ciphertext was encrypted, we'll have this cancellation here. And now we have another cancellation. So we are actually left with a message. Okay. I want to point out that when the identity is not the same, so when the identities don't match, of course, this formula for decryption is not going to give you the original message. But this is not all an adversary can do, right? So if an adversary that owns a secret key for a different identity may do different things. So how can we argue that knowing a different secret key is useless? So I'm gonna try to show you in the next slide. So consider an adversary who owns several secret keys for identity 1 to identity n of its choice. And consider the situation where this adversary is given this group element, which is a part of a ciphertext, the left part of the ciphertext. Of course, this is for identity ID star, which is different from all the identities for which he has a key. So now the question is, can this adversary compute the blinding factor in an efficient way? Or in other words, in a generic way? Because we are analyzing this in a generic model. So, okay, so our master theorem guarantees that if the following system of equations has no solution, I will explain it in a second. If it has no solution, then there does not exist an adversary that can win the generic experiment, and therefore we can claim the generic security of the primitive. So in this system of equations, you need to think of S, B, and A as symbols. S corresponds to the small s, B to beta, A to alpha. And what you can choose here is ID star. You can choose values for ID star, mu I, and IDI. And your goal is to make these two equations. Sorry, yeah, there we have an equality and inequality. Your goal is to make them both to satisfy both at the same time when you treat S, B, and A as symbols. All right, so yeah, I'm gonna show you how we can do this. So the first thing we can do is to multiply both sides by the same expression. So since we are multiplying by a symbolic expression, we had an equality before, if and only if we have an equality now. Okay, we can simplify the left-hand side by moving the big product inside the summation. So you can see that we have a division inside the summation that is going to be canceled by one of the terms in the product. And we left the right-hand side as it is. So what we have now is the equality between two polynomials in where the variables are, again, S, B, and A. So the question is, can we find polynomials that are equal here? Well, another very powerful rule that we can apply is to partially evaluate these polynomials. Because if two polynomials are equal, any partial evaluation of them must preserve the equality. So in particular, what happens when we evaluate these polynomials in B equals minus ID star? The left-hand side is going to become 0. And the right-hand side becomes what we have there. So we are almost done with this example. We just need to apply one more rule, which is, all right, we have a product that equals 0. A and S are symbols, they cannot be 0, so something inside the product must be 0. So we can say there exists a certain index for which that expression is 0. And yeah, so we are done because we have a contradiction, right? These two equations are contradictory. So after applying these steps, we have shown that you cannot actually find values for ID star, mu I, or IDI such that the equations hold symbolically. And that, after applying our master theorem, means that the primitive is secure in the generic group model. Okay, so in general, we have more rules. I mean, this was a very small example. And this is how our grammar looks like. So we can deal with disjunction, existential quantifications, for all quantifications, equalities, inequalities. Also, I want to point out that we treat us with big operators, sum and product, as symbols, because sometimes you need to capture uh, an arbitrary number of terms in a summation. So you need to deal with them as symbols. I also want to point out that this grammar is not perfect at all, and not all primitives can be expressed with this grammar. So those that cannot be expressed with this grammar cannot be analyzed with our tool. All right, so we have this grammar. In this grammar, we need to define the security experiment associated to the primitive, and then we have simplification rules. So these are some of the simplification rules that we use. We have, in the previous example, we have implicitly used the first one for getting rid of denominators. And we also have used, for example, in the last step, the one that is called zero prod, where a multiplication with a big operator prod is translated into the existence of one of the terms equals to 0. So our automated algorithm tries to apply these rules in certain order in order to find a contradiction, and this is guided by a heuristic. Okay, I'm gonna present some case studies. On the left side, you can see the scheme that we are analyzing. The first block corresponds to new schemes that we propose in the paper. Then you can see the time that it requires with the tool to be solved. And on the third column, you can see if they were proven or not. Okay, I want to say that, for example, these two cannot be expressed in our grammar. You could only uh, analyze a simplified version of them. And for example, these other two, the tool does not find a contradiction. So we would need more rules in order to make it work. But what we can do is to consider a fixed size version of these schemes, because these schemes are parametric. And if you consider fixed size, then the tool finds a contradiction, but okay, that's not very interesting in my opinion. The last column talks about security. Usually you want to argue many key security. That means, so the many key security is the case where the adversary owns many keys. And in some cases, we prove one key security, those with the asterisk, because that is enough to argue many times security. And this is proven in another result that was inspired by this work by Agrawal and Chase at Eurocrypt this year. Okay, so the last one is a scheme that is insecure. So I want to point out that we thought this scheme was secure. We were trying to prove it because we are using this trick of division and in such a way that things cancel out for correctness. And it really looked secure, but there is actually a non-trivial attack. So, and we found it with a tool. So yeah, so maybe the conclusion is that you need to be very careful when you analyze this scheme, and that's a motivation for having these automated algorithms. I also want to talk about, since we care about performance, we compare this petit IBE in the prime order version with 3 of the most efficient IBEs. And I mean, of course, this is not super meaningful because when you change the group, the elliptic curve, the numbers may change. But the conclusion is that this scheme can compete with the fastest ones. All right. And I also want to say that security here is not comparable because our scheme is proven in the generic group model, but the others are Bonnet Franklin is proven in the random oracle model, which is also not ideal, and the other two are proven selectively secure. So security is not comparable here. Okay, I want to finish by showing how the tool works. So I have some screenshots. So this how I don't know if you can see it. This is how the input file looks like. This is actually the input file for the example I showed you before. So the first thing you need to do is to define your variables and your equations. So maybe you can recognize the two equations that you had before. And then you can apply rules manually. So for example, this full simplify that it's basically takes your equations and puts them in normal form. In this case, it got rid of denominators and split things like in different terms. You can keep applying rules manually. So for example, just to show how this works, you can say substitute b by 0 in 1. It takes the first equation and applies the substitution. This I don't think this rule is very helpful for this example. But yeah, so you can apply rules manually, and you can also apply this go rule that is applying the heuristic. So this is trying to find uh, a sequence of rules that gives you a contradiction. So in this case, after applying this rule, we get, I don't know if you can see it in equation 7, 0 is not equal 0. That's a contradiction. So in this case, we are done. Of course, in general, this is not perfect. In general, the go rule may not solve your problem, but you can still apply rules manually, and you may solve it manually, and that's still something meaningful because what you have done is to formalize the security of your scheme using this framework. All right, so I'm gonna conclude. So in this work, we provide a new framework for proving security in the GGM that captures divisions in the exponent. Uh, okay, we have a tool for analyzing the symbolic experiments, and after applying our master theorem, that implies security in the generic group model. And we provide new constructions. I refer to the paper for those. And I want to finish by talking about future work. So from the theoretical point of view, it will be interesting to prove selective security under a Q-type assumption. So you improve the security model, you go to the standard model, but you only prove selective security. This could be done. And from the practical point of view, it will be interesting to explore synthesis. So, for example, if we could generate many primitives in certain modular way, for example, considering many polynomials for exponents of group elements, we could use our tool to filter those schemes and only get those that are secure, and then look at them more carefully. And yeah, so another very important future work, in my opinion, is to improve the expressivity of our grammar because it's not perfect at all. So it actually does not allow you to capture objects of second order objects. So, for example, quantifications over functions. But I think that's very challenging. It's a very interesting future work. So that was all. Thank you. No, that would be a generic result. So yeah, it's gonna be manually. It's gonna say something like if the scheme is in this. Well, we define that attribute-based encryption in a modular way, like a scheme of certain shape, and it will be a single result that proves that if you have a scheme of that shape, it's secure under the Q-type assumption. It's selectively secure under it's manually, yes. Yes. Yes, yes. But existential quantification is only about indices. So I think this order. I mean, it's of course not complete, but this order is the right one that you need for analyzing most of the primitives. So, in my opinion, the limitation of the grammar is a different one. It's the fact that we don't deal with second order objects. For example, when you say for all index in K, it will be very nice to say for all functions of indices. Yeah, it's very challenging, I think.